So welcome to the lecture on mathematical modeling. Today we will discuss about linearization of nonlinear systems. So in previous lectures we have performed mathematical modeling using transfer functions, and to derive the transfer functions for a system there was an assumption that transfer function can be derived only for linear time invariant systems. However, if we have nonlinear systems, we can't develop the transfer function. However, we know that there are several systems, they are in nonlinear range. Their behavior is mainly nonlinear. They are linear only in certain operating range. For example, if we have an amplifier, so initially it is linear, but then it saturates for certain voltage. If there is some electrical system like motor, this motor will not perform until certain input. It will perform only after certain threshold input, because it will take that to counter the friction in the motor. So we can see that for an amplifier, if this is input and this is output, so its relation is linear, but then it saturates after certain input. If this is motor, so and this is output and this is input, so this may behave like this. So initially there could be some dead zone, so no response, and then it will respond. If there are some dampers, so here is input, this is output. So damper behavior can be linear, and then it can become nonlinear. So we can see that there are several systems, they behave as a nonlinear system. But if we consider certain range like this part, here we can approximate it as linear. This part we can approximate as linear, and this part we can approximate as linear. So in this range we can apply the concept of transfer function. But if the system is working in this range or this range, so this is a nonlinear range of the system, and we can't apply the transfer function concept. However, if we linearize this nonlinear range, we can apply the transfer function. So this nonlinear range, suppose this is some point f x 0 x 0 and the system is operating about this point and in certain range. This range is small, so in this range we can approximate this nonlinear system as a linear system. So therefore, a linear system, what is the difference between linear system and nonlinear system? That linear system contain two properties, superposition and homogeneity. So linear system has this property, that is superposition and homogeneity. So what is superposition? So if I have a system, linear system, I give an input and I am getting some output. I am giving some different input and I get corresponding output. Now I give another input R to T and I get certain output C to T. And now for the same system I give an input R1T plus R2T. I should get an output that will be the sum of the individual outputs. So this is C1T plus C2T. So that is superposition, because the system is subjected to two different inputs and we are getting two different outputs. Now the sum of the inputs is applied, we should get the sum of the outputs. So this is superposition. Homogeneity is if we have this system R1T giving C1T and I apply an input K times R1T, I should get an output K times C1T, where K is some scalar constant. So if amplify the input, we should get the same amplification in the output. That is homogeneity. So there are several systems and this system behave as a linear system in certain range. So for the nonlinear system, if there is some operating point that we call equilibrium point and the system is operating in certain closed range of that operating point, we can approximate that system, nonlinear system, as a linear system. So how we can do that, we will see. So let's take this nonlinear system. Here input is xt, output is yt, and this is the nonlinear function y equal to fx, and this is the equilibrium point. The system is operating about this point. So we can write y equal to fx, we can expand as a Taylor series about this point. So the Taylor series we can write here so here we can write this Taylor series as the higher order derivatives of this function, and these derivatives d f by dx, d square f by dx square and higher order should be evaluated at x equal to x bar. So, at this equilibrium point at x equal to x bar, these values should be evaluated. Now, suppose this, because we assume that x minus x bar is small, because we say that the system is operating very close to this point. So, the input, what input we are giving is not very away from this. So, we are in a very small range. So, our x is varying about this point, maybe from this point to this point. So, it is close to this, and so our output will also vary in this range, so small range. So, we assume that x minus x bar is so small that the higher order like square, power 3, power 4 and these terms we can neglect because they will be even more smaller. So, we can approximate this as fx bar plus df by dx x minus x bar. So, we can approximate this. So, y bar equal to fx bar, because the value of function at x bar is y bar. So, here we can write y bar plus this df by dx is calculated at x equal to x bar. So, let us write this k and x minus x bar, or we can write y minus y bar equal to k x minus x bar. So, this is a linear function. So, this nonlinear function, this is now approximated as a linear function in close to this point. So, now if in any differential equation is formed that contain some nonlinear function fx, we can approximate this to linear function and then we can apply the Laplace transform and find the transfer function for this nonlinear system. Here we can see that there is only one variable x. Now, if there are more than one variable or two variables x1 and x2, then how to write this function? So, let us assume y is function of two input variable x1 and x2. So, here x1 and x2 they are two inputs and we are getting output y, and operating point operating input point is x1 bar and x2 bar. And y bar equal to f x1 bar and x2 bar. So, y equal to f x1 x2. Now, here are two inputs. We have to use the partial derivatives because there are two parameters x1 and x2. So, we can write this equal to f x1 x2 plus del f by del x1 minus x1 bar plus del f by del x2 minus x2 bar. This is the first derivative plus 1 by factorial 2 del square f by del x1 square x1 minus x1 bar square plus del square f by del x2 square x1 x2 minus x2 bar square plus some higher even more higher order terms. So this term is part of this first derivative, second derivative, and plus the higher order term. Now if we neglect these terms and higher order terms, assuming that this difference is very small, x1 minus x1 bar and x2 minus x2 bar, we will get f x1 x2 plus del f by del x1 x1 minus x1 bar plus del f by del x2 x2 minus x2 bar. Now these del f by del x1 should be evaluated at x equal to x1 and del f by del x2 should be evaluated at x equal to x2 bar. And so we can write, let's write this y bar plus del f by del x1 we say k1 x1 minus x1 bar plus let's say this is k2 x2 minus x2 bar, and we can write it y minus y bar equal to k1 x1 minus x1 bar plus k2 x2 minus x2 bar. Here k1 equal to del f by del x1 at x equal to x1 bar and k2 equal to del f by del x2 at x equal to x2 bar. So we see that this nonlinear function y is converted into a linear function about these operating points, and we calculate the partial derivative of this function with respect to x1, and we find the value at x equal to x1 bar, and then partial derivative k2 that is del f by del x2 at x equal to x2 bar, and we can put these values here and we can find for any input values x1 and x2 we can find the output y. So let's take one example to solve it. How to apply this? So we take one example. So we want to linearize the nonlinear equation or function z equal to xy. In the range five less or equal to x less or equal to 7 and y find the error of linearization. At x equal to 5 and y equal to 10. So, here we have this nonlinear equation or nonlinear function z equal to x y. So, we have two variables, input variable x and y, and it is said that they have this range 5 to 7 for x and 10 to 12 for y, and we have to find the error of linearization at x equal to 5 and y equal to 10. So, now here this range, from this range we should find that equilibrium point. So, let us take this equilibrium point as the mean of these two extreme values. So, here x1 x equal to x bar equal to 5 plus 7 by 2, that is 6, and this y equal to 10 plus 12 by 2, so that is 11. So, this is the equilibrium point, because at this point about 6 is equilibrium point and we are going to range varying from 5 to 7, and here 11 is the equilibrium point and we have this range 10 to 12. Now, corresponding to this point z equal to x bar into y bar. So, it is 6 into 11, that is 66. So, we are getting z bar as 66. So, now we just developed the equation for linearization containing two variables, and that is we can apply here, and so here z minus z bar equal to k1 x minus x bar plus k2 y minus y bar. So, this is the equation. Here output is z and two inputs x and y, and here k1 is derivative del f by del x, or we can say del z, because here f is z. So, del z by del x at x equal to x bar, and k2 equal to del z by del y at here y equal to y bar. So, we can find these values. So, here z minus z bar is 66 equal to k1. So, del z by del x, so del z is xy by del x, of course here y equal to y bar and here x equal to x bar. So, here we will get del xy by del x is nothing but y, and so y at y equal to y bar equal to y bar, and that y bar is 11. Similarly, we can find this. So del z by del y. So del xy by del y, and that is x at x equal to x bar, and that is x bar, and this is equal to 6. So we can write here k1 is 11, and then x minus x bar is 6 plus k2 is 6, y minus y bar is 11. So we can simplify this equation, and we can find z equal to 11x plus 6y minus 66. So this is the linearized form of the equation 1. So this 1 is the nonlinear equation or nonlinear function, and in this range we have linearized this as this equation number 2. Now you can see if we have this function in when we are in our differential equations, and we know that these values are in this operating range, we can replace this as this equation, and we can take easily the Laplace transform and we can obtain the transfer function, because now this is linear. Now the second question is find the error of linearization at x equal to 5 and y equal to 10. We have to find the lowest range, at lowest range of x and y, what is the error, how much error we are getting of when we are linearizing. So we can find this. So equation 1, we get z at x equal to 5 and y equal to 10, that is equal to x into y. So x is 5 and y is 10, so we are getting 50. So this is the correct value according to equation 1 following a nonlinear equation. Now from equation 2, we get z equal to, at the same x equal to 5, y equal to 10, 11 into 5 plus 6 into 10 minus 66. So we are getting 55 plus 60 minus 66, and we get here 49. So the error we are getting is 50 minus 49 upon 50, that is 1 by 50 or 2%. So we can see that when we are linearizing this at the lowest point, extreme point of the range, we are getting a maximum error of 2%. So here we learned that how to linearize a nonlinear system when the operating range is about some very close to some equilibrium point. So we can linearize that nonlinear system, nonlinear function about that range, and once we are able to linearize, we can be able to write the transfer function for that nonlinear system in that range, and that will help us to study the system using the transfer function. So here we would like to stop, and let's see in some next lecture. Thank you.